Okay, you see is the presentation going? You see
Uh,
that?
yeah, I
Yes,
see it. Yeah, yeah.
yes, yeah.
Okay, I'm going to start here. Today is July 2025. My name is Harry Ricker. I'm going to give a presentation, Fixing Einstein's Math. It's a continuation, part two. It's a continuation of a talk that I gave a couple of weeks ago. And I'm going to talk about Einstein's papers and use them as an examples of the mathematical procedure, basically, that I'm suggesting or proposing as a way to clarify a lot of what is going on in terms of Einstein's mathematics. And hopefully, if I can continue on, talk a little bit about the twin paradox and a lot of the confusing issues that crop up. Okay, so um, plan is to discuss examples from Einstein's papers and discover that the method used may have changed, but the conclusions remain the same as in the 1905 paper, even using Minkowski space-time. Okay, so they changed the math around. It made the equations look different, but it's really kind of the same thing. Okay, that's kind of my thesis for this particular part. Okay, I'm going to start again here to revisit my thesis from the previous presentation, that you need four Lorentz transformations. Maybe people are confused by the use of the term Lorentz transformations. These are simplifications of the complicated transformations that you see in the textbooks, and they've been reduced by evaluation um, to essentially the scale change laws. Okay, now I talked about there's the four equations that we're going to be talking about. There's actually eight, but there's four for time and four for space, so that gives you eight. And essentially, these are all the equations that you can come up with that could be used for transformations. And there are four perturbations. That's pretty much all there are. And then down at the bottom here, they have the general form T prime equals beta T, T prime equals T divided by beta, T equals beta T prime, and T equals T prime divided by beta. Okay, now the point of this, and the last two were derived by Einstein. So the ones that are in bold, T equals beta T prime, T equals T prime divided by beta, these are basically coordinate transformations, and what we'll be talking about today. So Einstein basically derived these equations that are in bold. Okay, and we'll talk a little bit about what the symbol T means. And there are transformations from the rest frame to the moving frame, but Einstein does it strangely, and that'll be one of the things that we'll talk about. Okay, this is a review of what I talked about in the previous talk, where um, T prime equals beta T is a basis transform, means 1 second at rest is converted into beta seconds in motion, and these are scale factor changes. So we're talking about the time scale. Okay, beta T equals beta T prime is a coordinate transform. That means the numbers of the time units, or the ticks on the clock, if you will, how many are counted. Okay, that's what a coordinate transform means. It means how many measure units are counted. And we have a transformation T equals beta T prime. That's says that the more units are counted in the rest frame than in the moving frame. And then we have a basis transform, which goes backwards from the moving frame to the rest frame. And it says that the um, time units are shorter in the rest frame than in the moving frame. And then the last one is coordinate transformation, and it takes coordinate measure in the rest frame into the moving frame. And we find out that there are fewer seconds counted in the moving frame than are counted in the rest frame. Now, these are highlighted in bold because these are these two transformations, these two coordinate transformations are what Einstein derives. Okay, I'm going to talk about the 1905 paper. I'm making this, I'm not going to cover all the details. I'm just going to talk about his time transformation. And what he does is he spends a lot of time talking about synchronization of clocks and all this stuff. And finally, he gets to the Lorentz transform, derives the Lorentz transform. And then he says, okay, now I'm going to show what this Lorentz transform, I'm going to apply this Lorentz transform theory that I've developed in the previous parts, and I'm going to apply it to the transformation of time. He also does space first, but time after, but we're talking time today. Okay, so what he does is he derives the Lorentz transform, then solves it for x equals vt. He doesn't tell us why he does it. It's kind of a mysterious thing. But he derives the coordinate transform equation that I talked about earlier, t prime, okay, the time on the clock in the moving frame is equal to time on the clock divided by beta, okay, in the rest, well, time on the clock in the rest frame divided by beta. And so what he comes out is he says that there's less time counted on the moving clock. So the clock in the rest frame, fewer seconds are counted, and that's what this equation means. That's the coordinate equation. Okay, now this is where it gets a little ambiguous. He says that this time on the clock in the moving frame is viewed from the stationary frame. Okay, and this word stationary frame kind of causes kind of confusion because how did he get this equation by putting in x equals vt? Well, that's kind of a mysterious thing. Doesn't really explain how that happens. Okay, then he gives us three examples of what this means. They're famous examples. And the first one is that if we have two clocks at A and B along a coordinate system, if I move one of the clocks from A to B, then there's a difference in time between when the clock moves from A to B. I'm simplifying it. That's kind of mysterious. Why does the time on the clock change when it's moved? Okay, that's supposedly explained by the fact that the clock coordinate time, the clock rate changes, or the time that's recorded by the clock changes when it's moved through space. Okay, then there's another example where he has clock moving around in a polygon, and he says that the clock loses time when it moves around the polygon. And then he's got a third example where he says that a clock at the equator loses time compared to a clock at the poles. And he gives those three examples. But he never gives those three examples again. And a lot of people have focused on these three examples that he gives, and there's a lot of debate about it. And, but he never really discusses them in his later papers. So you're sort of left wondering, did he really mean these things? Or were they mistakes that he later neglected to discuss further because he wasn't really satisfied with these examples that he gave? So that's a problem. Okay, I infer what he means is that the number of unit seconds, and I talked about this, the number of unit seconds counted during a fixed time interval defined on the stationary clock is less for the moving clock. Okay, so that's what this means. Okay, that's the conclusion. So this is a coordinate transformation. Okay, what is meant by coordinate transformation is coordinate means the counting the number of units of measure units, counting the number of measure units. Okay, 1907, moving through this pretty quickly. He kind of now says, wait a minute, what I said in 1905, I'm going to tell you something completely different now. Okay, that's kind of a, so most people don't even look at the 1907 paper. Everybody quotes the 1905 paper, and all the textbooks quote the 1905 paper, and it's like this 1907 paper never really existed. Okay, but he gives us a different equation. Okay, T equals beta T prime, and tells us that this means that an interval of time measured in the rest frame is longer than measured in the moving frame, from which he infers that the moving clock is dilated. That's that's really strange. I'm sorry to tell you. And it seems kind of backwards. And so this is kind of another example of kind of the confusion that Einstein creates by the way he phrases things and talks about things. And Roger Anderton has been talking about this for years. He says that the theory of relativity is ambiguous. This is another example of how it gets ambiguous. Um, okay, then he transforms frequency from the uh, 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 frequent and the frequency and says that this is confirmed. I think I've jumped a little bit ahead here. All right. Anyway, he transforms into the frequency dim. Okay, so what he does is he uses this equation T equals beta T prime, and then talks about how this means that the clock in the moving frame is slow. Okay, and then he says that this guy Stark has done experiments on moving candle rays, and that confirms that his theory of relativity is correct. Now, primarily, I think the main motivation for this is because he wants to claim that his theory is confirmed by these experiments. So the candle experiments are when you accelerate an atom to a high velocity, the frequency, the frequency radiated by the atom is shifted when it's accelerated. That's Clark's experiments. So he says that's a proof of my theory. Okay, then he has a proof that he does this, and he compares the numbers of counted time units in the moving frame. So what he, remember here they had this equation T equals beta T prime, which says that the number of counts in the rest frame is longer than in the moving frame. Well, the time, he doesn't say the counts, he says the time is longer in the moving frame. Well, what he does is he then starts talking about the ticks on the clock. Okay. So he says that the number of ticks counted on the moving clock is fewer than are counted on the rest clock because of this equation T equals beta T prime. And says, therefore, the frequency is lower for the moving clock. Okay. It's kind of hard to understand what he's doing there because it's he doesn't when you start looking at his equations, he doesn't explain what he's doing with these equations and why he's putting up these equations as typical obscure physics. In the 1910 paper, so now there's another paper published in 1910. Okay, and he gives a better explanation as to what he's talking about. So that's kind of helpful, that if you were kind of confused by what he did in 1907, 1910 paper, you can refer to that paper and it's much clearer as to what he's doing. Okay, so what he does in the 1910 paper is, and this is kind of interesting, and you have to be aware of that, he does a completely different derivation of a Lorentz transformation. And he doesn't do it by this business of the speed of light is a constant and talking about synchronization of clocks and all this stuff. He just says, okay, I'm looking for a transformation of variables that makes the light travel equations to be the same. So in other words, it's kind of similar to what you see in modern textbooks where they give you this algebraic derivation of the Lorentz transform. That's the first time it shows up in this 1910 paper, and Einstein does it. Okay, so if you wonder where that comes from, it came from Einstein. Okay, so he derives the Lorentz transform by this method of algebraic method, an algebraic method different from the previous method in 1905 and 1907. Then he says, oh, I'm going to change the symbols in my Lorentz transformation. I'm going to exchange the prime symbols for the unprimed symbols. Okay, and because of the principle of relativity, this means that now I've changed from the rest frame where the Lorentz transformation was derived into the moving frame by this exchange of symbols. So now he has what in the textbooks they call the inverse Lorentz transformation. Okay, now what he does, well, he did this in 1907, but and I want to mention that to you. And this part is clearer where he does it. That's why I'm pointing out 1910. It's clearer. Then he derives the transformation t equals beta t prime by setting x prime equals 0 in the inverse Lorentz transformation. Okay, so this is a key step, setting x prime equals to 0. Now, a lot of people argue about what this means. We have a big argument about this in some of the email exchanges. What this means is that he's using the moving frame as a reference. So the reference clock is in the moving frame. Okay. And that's what setting x prime equals 0 means. That means that we're using the moving frame as our reference clock. And it's kind of hard to explain why this is the case. And if you want to talk about it later in emails, and we can discuss that. Okay, then he defines a clock period, and he breaks it up into periods. And here we have, and he calls a period, a unit period as P0. And then he sort of adds up all these periods, these little periods of the clock. These are ticks, if you will, the periods of the oscillation. The clock has a harmonic oscillator in it that has a period, and it's ticking along, and the clock is counting these periods. Okay. Now, what he does is then he counts these periods of the clock. Okay. And now this is kind of an important thing that I want to talk about, which is that he writes this equation where the time interval, let's call it T0, equals beta Tn. So now he's saying that these periods of the clock are what is transformed by this equation, T equals beta T prime. So now we know that it is a coordinate transformation because the coordinate transformation is counting the number of periods of the clock oscillator, or if you will, ticks of the clock. So in other words, the total time is the total number of clock ticks. Yeah, right. That makes sense, right? Now, he's of course saying that there are fewer clock ticks counted in the rest frame relative to the moving frame, which kind of gets you into kind of it's kind of confusing. So this is what he says. Observed from the moving clock, the rest clock reads P equals P0 divided by beta in a unit time. So there are fewer of these clock tick things counted when the moving clock has a unit time. The rest clock, this is so confusing. In other words, a clock moving uniformly with velocity v with respect to a reference system runs as observed from this system 1 over beta times slower than an identical clock that is at rest with respect to this system. Do you understand that? That's a direct quote from what Einstein said. That's a direct quote. I didn't make that up. That's what he said. If it's confusing to you, Welcome to the club. All right. Now I'm going to talk a little bit about, reading this. What's confusing about it? Well, I said last time I talked here that Einstein does things backwards. And so what do you mean backwards? Well, this is an example of him doing things backwards. He defines the transformation in the moving frame, okay, and then goes backwards into the rest frame with this transformation t equals beta t prime. And so it's actually the rest clock that's the reference clock that's making the measurement. So the observer in the rest frame is observing a clock in the moving frame. And so it's the observer's clock in the rest frame that's the reference clock. Okay. And anyway, it's so confusing. Okay. So he goes backwards. He defines a rest frame, but then he defines the Lorentz transformation for the moving frame. And then he goes back to the rest frame. Why didn't he just start it in the rest frame in the first place? Why all this back and forth? It's confusing. Okay. Then he makes the statement, the clock in the clock in the moving frame as viewed from the rest frame. Okay. What does that mean? What does it mean? The clock viewed from the moving clock viewed from the rest frame. Not clear what that means. So that's leads to later confusion. Okay. So we don't know what that means. Basically what he's saying is there are more periods of oscillation in the rest frame clock than the moving frame clock, but we don't know what clock is the reference clock. Okay, it's kind of confusing. How do we know the rest clock is not changed? And it's kind of vague. I find it hard to really understand. That's basically my point. And so we're going to try to see if we can figure this out here. So I've come up with a simpler method. We're going to use my approach. Okay, my approach. And so in my approach, we start from the Lorentz transformation, okay, which, well known. And we're going to evaluate the Lorentz transformation for time, the Lorentz transformation at time at t equals 0. Okay, we're going to set t equals 0 in the Lorentz transformation. I'm sorry, I think I got that wrong. Should be x equals 0. Evaluate at x equals 0. Said that wrong. Sorry about that. And then we get this equation, t prime equals beta t. That's a basis transform. Okay. That's the basis transform. All right. It says that the unit seconds in the moving clock are longer than the unit seconds on the rest clock. Okay. Well, what does that actually mean? Well, it means the moving clock is slow, but we did it more directly here. I mean, we didn't go through all this business of having to derive the inverse Lorentz transform and then setting the x prime equal to 0 in the Lorentz transform, and then getting the transform from the moving frame to the rest frame, and then counting time on the clock in the rest frame. We just start from the rest frame and find out how time is changed in the moving frame. Okay, now we can verify that the rest frame clock frequency is lower than the moving frame clock is running slow compared to the rest frame clock, which means the frequency of a moving candle ray is going to be less than the frequency at rest. And it's very easy to do. All we have to do is take this t prime equals beta t, which is the basis transform, and convert it into frequency. And when we do that, we get the frequency of the rest clock is higher than the frequency of the moving clock, meaning basically since the frequency at rest is higher than the frequency when it's moving, that means the moving frequency is low. Does everybody understand that? It's pretty straightforward. So we didn't really need, so my point, well, what's my point here? my point is it was a lot easier to do it my way because in my theory, we already know we already know the difference between the basis and the coordinate transforms. Einstein doesn't know that there's anything called a basis transform. He's only looking at this, how do the hands on the clock change? And that's he's sort of in effect basically what we'd call today fudged. He's fudged to, by putting x equals vt in 1905, he fudged to get the result that the moving clock is running slower because its hands are moving slower. Okay, the hands aren't moving as fast as the hands in the rest clock. And because Einstein's living in an era when we're talking about clocks with hands moving on them, we have these terms faster and slower, hands moving faster and slower. Okay, this slide here really basically shows that if you use the coordinate transform and you convert that to frequency, it turns out you don't get the correct frequency result. Okay, so what that means is that there's a difference in how you have to deal with the coordinate transform and the basis transform. You have to understand what they're transforming, and you have to understand what the symbols mean. The symbols don't mean the same thing in a basis transform as the symbols in the coordinate transform. And this is really a source of a lot of the problem when you talk about Einstein's theory and Solari's theory. We're going to run into that runs into a similar problem. There's paradoxes come out of this, okay, because not paying attention to the difference between a coordinate transform and a basis transform, Einstein mixes them up. And because he does that, when you mix up the coordinate transform with a basis transform, what happens is you get paradoxes, okay? And the theory of relativity, special relativity, is famous for its paradoxes. And there have been arguments, it's been over 120 years now since 1905 paper. There's, many proposals have been put forward to explain these paradoxes away, none of them very satisfactory. Okay, now I'm going to talk a little bit about the, if we use this kind of a summary of it, using Einstein's discussion, it is unclear what he means since he defines time in the moving frame, but observes time in the rest frame. Okay, there's this ambiguity, and it leads to the interpretation that time as perceived by an observer, this is a quote now, time as perceived by an observer appears to flow more slowly in systems in relative motion to himself. That's a quote from Einstein. Not sure what that means. So clocks in motion don't run slow. They only seem to run slow to an observer in the opposite frame. Okay. If you're not aware of this, this is another one of the big controversies about his theory, which is time really slow for the clock in the moving frame, or does it just appear to be slow to the observer in the opposite frame, or what we would call the rest frame? Okay, so what is it? Is the clock really running slow, or is it only appear to run slow? Okay, so this is a big controversy. This is one of the big ambiguities. Okay, I use the term projective interpretation. You could use the term. The reason I use projective is because that's a mathematical term. Okay, some people use that it's a function of perspective. The observer, from the perspective of the observer at rest, the moving clock appears to run slow. Okay, now then there's the problem here that you have, which is, well, if it's only a effect of perspective of the observer looking at the other clock, then how can you say that a traveling twin ages less than a stay-at-home twin? So, and then that's also in conflict with the examples that he gave in his 1905 paper. So if you're not confused by now, okay, Hopefully we can clarify some of this stuff. Okay. So then you have the other part was in his example where he has the clock traveling around and coming back to its starting point in his 1905 paper. He says the clock reads behind what it should have read with the clock that didn't move. But if it's a prospective effect, then that shouldn't happen. So what's he talking about here? You've got, he just seems to be confusing things. Okay. Um, uh, Here's my summary. We got hopefully going to squeeze this in. I'm not sure how many minutes we got left, but it's getting close. So the conclusions: Einstein's method is not convincing because too many steps to follow. And I told you, he derives the Lorentz transform, then converts to the inverse Lorentz transform, and then he puts in x prime equals 0. And then he says, well, we're going to, as viewed from the clock in the rest frame, the moving clock, I mean, it's just back and forth. And so we have this problem that he starts in the moving frame to talk about what an observer in the rest frame sees. And that doesn't really make sense. Not clear what he's talking about here because you got two different interpretations. Does the clock in a moving frame really run slow, or does it only appear to run slow? Okay, and so then finally at the bottom here, we only have 2 of the 4 transformations that I've been talking about. So his theory is kind of incomplete because he doesn't get all of the transformations that I have in my theory. That is an attempt to sort of clarify a lot of the confusion. Okay, so that's kind of the end. We're coming up on. I'm going to continue on with another with more of this discussion. So if anybody's got any questions or issues they want to, we got about 6 minutes before we time out. So if you got any comments or questions, you can go ahead now. Go ahead.
Unmute. Right. So that I take because James Keane made a interesting comment on the last talk on Saturday, in that we sort of all agree that special relativity is wrong. So we want to get out of this the basic framework that's necessary for a new theory, or a. So one of the things I've thought of is that special relativity can't exist without gravity. So you have to put it in a theory where it is a approximation within another theory. So
well, you're not asking questions about the presentation. You're kind of basic.
Well, yeah, but that's a comment. You can agree or disagree, and also when you go back to your start, you had this problem about which is a stationary frame, which is a moving frame. In all sort of, or most textbooks, they have a analysis of the Michelson-Morley experiment where they say the ether wind. So they take the Earth's surface as a stationary frame and then have an ether wind coming through it. And so before you start the analysis, you've already done a Galilean transform, which you're later going to be proving that it's inappropriate. So in a way, you have to start off either believing that there's an ether frame that's stationary, absolutely, locally, or there's something else stationary, because the Earth's surface is not stationary. So that's my 2 points.
All right, I'm not okay. What this is about is trying to clean up the math. The title is Fixing Einstein's Math. What this is about is trying to clean up the math. Okay, you've raised physical model issues. Okay, once we have the math cleaned up, then we can say whether or not the math matches a physical model. As it stands now, okay, what they did was they took this bizarre set of papers and that were confusing, ambiguous, and not really clear what he was talking about. And they said, oh, and here's some experiments that demonstrate this theory is correct. So, but the math isn't clean. It's just a mess. So if you don't know, if you don't have a clear, well-defined, rigorous system of mathematics that's correct, you can't really apply it to a physical model and say the physical world acts in accordance with this theory. The theory doesn't have a well-defined math model behind it.
Yeah. And one of the things you said in his paper, which is that the clocks tick differently at the pole to the equator, is wrong, because they all tick at sea level. They all tick the same rate on the Earth's surface, because the gravitational and the spin work together to give you the same. So if you don't have a theory of gravity in your thing, you'll end up with conclusions like Einstein made in his, was it the first paper that's wrong, or second, or 1907 paper?
Like I said, that example doesn't appear in later papers, and so that's one of an example of, red herrings. Is that a red herring? Was he really talking about that? Did he really mean to say that, or was he just speculating? It doesn't appear in his later papers. So is that really a valid thing to talk about? Is it, can you use that to prove his theory is correct? The only thing really that you can say that offers a proof is the Stark, the Candle ray experiments. That was confirmed by Ives and Stilwell to a much higher degree of accuracy in the 1930s. And so you could say that's really the proof, the experimental proof there. The problem is that in order to accept that, you have to go through this tortuous method that he uses in 1907 and 1910, where he counts ticks. And he says the frequency is less or lower. The clock is slower in the moving frame because the clock in the moving frame counts fewer ticks. That's essentially his argument, which in my mind wasn't a very satisfactory argument, which is why I actually did the conversion from time to frequency that I showed you. And I showed that you have to have a basis transform to calculate the frequency change correctly. You can kind of infer it from the coordinate transform, but I never found that argument to be convincing. So does that help you any? We're coming up. Let's see, we got less than a minute.
I'm just pointing out the fact that as soon as you start trying to make some sense of special relativity, they say, oh, but general relativity cures all these problems anyway. So, and we always come up with the problem in the GPS that the actual all.
Okay, I'm now going to talk about I'm going to talk about Einstein's 1911 paper. I'm moving through this pretty quickly because there's a lot of stuff here to unpack, and I don't really want to do it in the upcoming weeks, and so I'm going to try to pack it all in if you guys don't mind. Okay, am I up and going?
Yes.
You see this thing? All right. So here we're going to talk about the 1911 paper. Wow. We've talked about the 1905 paper, the 1907 paper, the 1910 paper. Now we have a 1911 paper. Wow. And guess what? He's going to tell us something different. Okay. And if you want to look at these papers, I think there's a website, Einstein's papers, that you can go to. I think it's run by some Israeli University of Israel or something that has his um, copyright, that owns the copyright to Einstein's work. Okay. Now here's the kind of the thing is, this paper is a little bit different in that it's a talk that he gave. It's not very mathematical. He's just kind of summarizing things. Okay. He's just giving you an overview of his theory. And one of the things that's interesting about it is that there's a question and answer section appended at the back. And if you're interested in some of the questions and answers are kind of insightful, okay, and they kind of put him on the spot, but he manages to whittle out and kind of doesn't really give clear answers, in my opinion, to some of the questions that are proposed. So if you're interested in that, it's well worth answering. But here's the point of this 1911 paper. He talks about he introduces what we would call today the twin paradox. Okay, so he doesn't actually present a twin paradox, as we'll find out, but it's kind of the nucleus of the idea. Okay, so again, he talks about the inverse Lorentz transformation and solves it for x equals 0. So we're in the moving frame, okay, and we're solving for x equals 0 and the Lorentz transform. So it's the moving frame that we're starting from. And as I pointed out before, he uses the substitution x equals vt in 1905. Well, it turns out x equals vt is the same as x equals 0. Okay. And I don't know that a lot of people really understand that, but that's really what's going on there. So x equals vt means the same thing as setting x prime equals 0. Okay, which means you're going to get, as your result, you're going to get a coordinate transformation. And so then you get this coordinate transform pair, t prime equals t divided by beta, which says that the number of seconds recorded on the moving clock is less than the number of seconds recorded on the rest clock. And then you have the inverse of that, which is that the number of seconds recorded on the rest clock is greater than the number of seconds recorded on the moving clock. And these are dial readings. Because they're dial readings, we know that they're coordinate transformations. Okay. Again, he's solving the problem backwards from the moving frame to the rest frame. And, we have the same problem that I discussed previously about, why you're viewing the clock in the rest frame. So your reference clock is in the rest frame and you're looking at the clock supposedly in the moving frame and ascertaining that the moving 1 second in the moving frame equals beta seconds in the rest frame. And so the moving frame clock is slow. Okay. And then you have that problem that I talked about before, which is, what does this mean? Does it mean that time is the same in the moving frame, but only appears to be slow in the rest frame? Or is the clock in the moving frame actually running slow? Well, we don't know. Okay. So that's our preliminary discussion, which was a review of what I talked about earlier. Okay, so I'm going to talk a little bit about what Einstein says that kind of leads us to this twin paradox issue. He says, the thing is at its funniest when one imagines that the following is done. One imparts to the clock a very great velocity, almost equal to c, then lets it fly on in a momentum in the opposite direction. So he's saying that we're going to have this clock fly out and then we're going to have it turn around and come flying back. And then he says, it turns out that the position of the clock's hands have hardly changed during the clock's entire trip. Well, that follows because he's using the coordinate transformation, and according to him in his equation that we talked about, the hands of the moving clock barely move compared to the hands on the rest clock. Now here it comes. He says an organism in a box would return. So we put some kind of organism. He doesn't tell us what. Would have undergone a small change. In other words, the organism in this box that's gone back and gone out and come back at close to the speed of light. It's not going to age because the hands on the clock didn't move. So because the hands on the clock didn't move, the organism in the box isn't going to age. Organisms at rest have long since given away to new generations. So in other words, when the organism in the box, he doesn't say human, just says organism. He's the putting the human or the astronaut into it. The twin paradox part that gets put in later by other people. So he's saying that twin gets out there, he's accelerated to the speed of light, and then when it comes back, the organism is still alive, but organisms that were at rest on the earth have all died and passed away. And that's all right. Okay, what's the fallacy? Okay, the moving hands on the clock implies the duration of biological time or the aging process. Well, there's no proof that just because you imagined a clock, okay, so we don't have an actual clock, it's an imaginary clock that's based on his Lorentz transformations. And so he's saying that hands on the clock, the moving of hands on a clock is equivalent to biological aging. No proof of that. Doesn't take into account why the clock hands change slowly. So he's not really looking at the problem completely. He says the ticks occur more slowly. Okay, yeah, that seems to be a valid conclusion of your coordinate transformation. Then this is it here. He conflates clock readings with duration of time by assuming time is what a clock's hands indicate. Well, he hasn't proved to us that what a clock's hands indicate actually is time. He just assumed that. So he assumes that the duration of time has changed, not the time measuring process. So we have this. So what I mean by that is he didn't really look at why the ticks are longer. Okay. Well, if the ticks are longer, there's fewer ticks, then doesn't that mean that the ticks are longer? But he assumes that the time of the ticks doesn't change. So in other words, the duration of each tick, according to Einstein, doesn't change. Okay. So fewer ticks means less time, less total time has elapsed. We're going to find out that's not true. Okay. Then here, in this paper, he goes on to talk about Minkowski's theory. Okay, and Minkowski at this point has proposed this, his theory of space, which we now call space-time. He calls it a highly interesting mathematical elaboration that the theory has undergone. So he said, highly interesting mathematical elaboration. That's interesting. I thought that was interesting. Notes that his theory of Minkowski, time is an imaginary variable instead of the time variable t. So, he kind of points out that the time has become an imaginary variable in Minkowski's theory. It's this, ICT thing has gotten into the theory. So we're not, so what does this really mean? We have imaginary time. But Einstein doesn't really address that issue. He just points it out to us. Okay, now we have Fritz Mueller's question. So I mentioned earlier that there were questions. People had these questions. And Fritz Mueller puts forth this question. He says, How can the reading of a clock making a round trip be different when it returns to the starting point, given that a moving rod retains its same length when returned to its starting point? So he wants Einstein to explain the difference between what happens to a moving rod and what happens to a clock. Fritz Mueller thinks that a clock should return with the same time reading on it, just like when a measuring rod returns to rest, it's measuring the same length as before. And Einstein says, it is impossible to assume that after having traveled along a polygonal path and returned to point A, that the clock will again be running synchronously with the clock that has been at rest at point A. I don't really think that's an answer. Okay. All right. Now, the reason I brought that up is because I'm really not very satisfied with Einstein's explanation. What does he mean by synchronously? Never really, we don't know what synchronously means. Now, he doesn't really tell us that the clock is running at the same rate when it's back at rest than when it was moved, when it left. So you might think about that. Maybe if the clock is the clock running at the same rate when it returns as it was running when it left? He doesn't really address that issue. He just says that the clock reading has changed, but doesn't really give us a very good reason for why. So he says the hands read differently. Maybe the clock rate is different or not. He doesn't tell us. Okay, so having said that, I'm going to try to sort of clarify some of this stuff here. The point is, Einstein doesn't take into account the basis change law. Okay, and I remember I started off by talking about there are four laws, four transformation laws. Two of them are basis transformations and two of them are coordinate transformations. He doesn't take into account at all whether or not the ticks on the clock are changing. He assumes the ticks on the clock are the same. So there's no change in the time scale that defines the oscillations of the clock. There's no change there. He assumes the basis change laws don't exist at all. So that means there's no change in the definition of a second on the clock. Okay, so based on that, he says because the hands are different, therefore time is different. Okay, I don't think that's correct. Okay. All right, so if we take into account that ticks are different according to the basis transform, we find that the ticks are longer, okay, but there are fewer ticks. And if we multiply the fact that the ticks are longer by the fact that there are fewer ticks, we're going to get the same time interval. So going back to what I was talking about in the previous presentation, there's all these time intervals that you add up. Those time intervals are going to be longer, okay? And Einstein doesn't take that into account when he says the organism in the box is going to be aged less than organisms on the Earth. If we take into account the fact that the ticks are longer, although there are fewer ticks counted, the time turns out to be the same. So there's no difference in the duration of time. It's just a difference in what the clock measures. So if we take that into account, the moving clock is basically the same time interval as occurs for the moving clock as occurs for the rest clock. There's no change in time. There's only a change in what the clock indicates. Okay. And so I'm going to talk disagreement between the length of a rod is it's unchanged, okay, when it returns. Well, the clock's rate is going to be unchanged when it's returned, but its reading is going to be different because it's counting the ticks continuously during its journey, and it's counting fewer ticks when it's moving. But we have to take into account the fact that the ticks are longer that it is counting. And Einstein doesn't take into account the fact that the ticks on the clock are longer. He only takes into account the fact that the ticks are fewer. Okay. And then, of course, now we have the ambiguity of which clock is moving and which clock is at rest. That's a classic example of the twin paradox. Okay, so, right. Now, do you want the proof of this? Well, we'll go through it a little bit here. The duration of a time interval measured by the clock is, well, we'll call it T, and we'll say that T is equal to P, the period of a tick, times the number of ticks. P is the fundamental period of the reference oscillator, and N is the number of oscillation of clock ticks. Okay, by the coordinate transformation, T is the number of periods or ticks counted by the clock. So we're going to say T is equal to the number of ticks. And then we're also going to say that T prime and N prime. So we're going to say that N prime is the number of ticks in the moving frame, and N is the number of ticks in the rest frame. And so then when we make this identification, the transform for the change in the length of the fundamental clock period, T prime equals beta T. So now we have that the period in the moving frame is beta times P. The moving period is longer. The time interval for the moving clock is T prime, okay? And that's equal to the number of ticks times the length of a period of the tick, okay? And when we apply the transformation, N prime equals N divided by beta, and the period law change is P prime beta times P, and we multiply those two together, we get that N prime P prime equals NP. So in other words, there's no change in the period. The time doesn't change. It's the same. Okay, so T prime equals T, meaning that the time interval that occurs in the moving frame is equal to the time interval that occurs in the rest frame. And therefore, time is an absolute invariant measure. There's no change in time. Okay. Einstein's method produces confusion regarding what is changed by motion. So there's no clearly defined rest clock. That's part of the confusion in his theory. What's the rest clock in his theory? Because any clock can be a rest clock, whether it's moving, doesn't make any sense. The differential aging discrepancy is a mathematical flaw in the method used. So there's really no change in time. All he did was he didn't take into account the fact that the ticks on the clock are longer. He assumed the ticks on the clock in the rest frame were the same as the ticks on the clock in the moving frame. And because the hands were different, therefore he said that time was different. But that's not correct, because he didn't have all the transformations that he needed in order to make his theory work correctly. Okay, then we have the contradiction with statements that for a co-moving observer, there is no rest change. Okay, so now we have a couple of problems here. And when he was talking about length, he said that an observer moving with the rod in motion doesn't observe that the rod is contracted. Okay, and so then I'm thinking to myself, well, why isn't that true for a clock? So an observer who's moving with the clock in the moving frame, he doesn't observe that his clock is different.
No, he doesn't.
Right, because his theory's screwed up. It's a screwed up. So, what is he talking about? Is he seems to oscillate between that the difference in the clocks is a perspective effect, or is it that the clocks are changed actually by motion? So is the clock ticking slower in motion, or does it only appear to be ticking slower in motion? And now you have the flaw that for the twin paradox to be true, you have to assume that the clock is actually ticking slower in motion, okay, in order for the organism to be returned at a younger age than organisms on the Earth. But then that's kind of contradicted by the fact that he's saying that a co-moving observer doesn't see a change in the clock, okay, nor does he see a change in the length. So what's he saying? Which one of these two things is true? Well, that's more confusion. Okay. So in my opinion, there's no twin paradox, primarily because mathematics is wrong. That's basically the bottom line. Okay. So this goes back to the discussion that we had earlier, which is, how can you make a conclusion about a physical theory if you don't have the correct mathematics to compare against your physical theory? And special relativity doesn't have the correct mathematics.
Okay, anyway. Just make a comment, because I disagree with you, because not that Einstein didn't get things clear. I agree with you that in that respect, but what we're trying to uncover is to see behind our measurement system, because all we see with our measurement system is the ratio of two lengths, or the ratio of two times in any particular frame, the ratio of two speeds, and any variation, the relativity factor is only seen when you compare two different frames. So once you make a measurement in any frame, whatever they are, moving relative to each other, they'll always be the same, because there's a ratio happening. And that's my opinion. And we should put this all in dimensional analysis where it belongs, because, and this is what O'Reilly was trying to say. I just did
that. That's what this whole presentation is about. It's about the dimensional analysis. And when you do the dimensional analysis, you find out that there's no difference in the length or the time.
Yes. But when you do a ratio of if you can, like time, you can infer the time that's going on in a different frame from another frame, whether it's moving fast or slow or whatever.
The clock is apparently not running at this, is apparently not indicating the correct time.
Yes, and that is a measurement truth, because that we do it all the time in GPS, etc. Well,
but that doesn't mean that the time has changed.
No, because we only measure time in numbers in a unit, and when they come back and compare numbers, they'll see that there's no disagreement in what the speed of light is, or all the constants of nature are, etc. Because your units haven't changed, because they're all ratios.
And their assumption, Einstein makes the assumption that the units don't change.
They don't.
Okay. And because based on that assumption, when you get different measurements on the clock measurements have changed according to his theory. He doesn't take into account that the units also are changing. That's why you need the 4 transformations. You need the basis change transformations and the coordinate change transformations. You need to look at all of the transformations. He only looks at the coordinate changes. Now, this gets more complicated later, which I'm not really getting into, when the light clock, when you talk about the light clock gives you the basis change transformation. It gives you T prime equals beta T. Okay, and so some books try to base the theory on the light clock, okay, as being the example of how time changes. And that's kind of confusing because they're using a different transformation than the coordinate transformation.
The maths is all messed up because we can see mesons have a longer life. We can observe the different speeds and the lifetime changes. We can, in a calorimeter in the big particle accelerators, we can see that the mass of a fast moving electron is greater than the mass of a slower moving electron. So, but that's our frame comparing with a moving frame. So it's always necessary to compare one frame with another to get your ratio, and then, but within each of those two frames, if you could get a measurement lab onto a meson or whatever, you could, all your results of all the constants of nature will be the same. So it's the maths in comparing two frames.
That's an assertion that comes from Einstein's claim.
Yeah, well, it's basically dimensional analysis that tells you that, because that's the way that when you create a ratio of two numbers with a relativity factor in the same frame, that relativity factor cancels, and so everyone's going to get the same number.
Let's go back to what the Lorentz transformation basically tells us. The Lorentz transformation is basically telling us that that the laws of physics, particularly the Maxwell equations, are basically the same when we use the transformed variables. Okay. And so what that allows them to do is to allow them to use the laws of physics. Okay. They've converted it into 4 vectors. And what it allows them to do is allows them to use their Newtonian equations suitably adjusted by the Lorentz transformations. Do you understand what I'm saying here? In other words, what the Lorentz
problem is that you don't have laws of physics anymore if you're using a Lorentz or other any of the 4 transformations you talked about, because time is used as a position coordinate. It is therefore no longer an independent variable in the laws of physics. So you don't have any laws of physics. So, this whole myth about Lorentz invariance is basically a myth.
Well, yes and no, depending upon your point of view.
Why is a Lorentz transform required in any case in science?
Because it allows them to do calculations using the existing Newtonian laws of physics for high-speed physics when that the laws don't really apply in the high-speed physics case. So that's why they adopted.
What example of that exists in science?
What example?
Well, an abstract description.
He just cited one, which was the muon decay example. Although I don't think that's a very good case. But
so we don't have any good cases. Okay. So
no, Jeff, no, you're wrong. Okay, they use these energy momentum equations in particle physics, where they call it relativistic dynamics cases, and they use Newtonian's laws, the laws of conservation of momentum, the laws of conservation of energy, and they use all those Newtonian laws, but they don't use them with the same variables. They don't use the rest variable, the rest mass in the calculations. They use a relativistic mass in the calculations, and that relativistic mass is adjusted by the Lorentz factor beta. Okay, and so when they change the scale. They, in effect, basically, they're doing a scale change adjustment, just like for time. So for instance, time is changed by the basis equation. So the time on the moving clock is said to be longer according to T prime equals beta T. So what they do is when they take mass, they adjust the quantities in the equations, like mass is calculated as being a different mass. So they use a different mass in the equations calculated by the beta factor. And when they do that, the equations work. That's why they're using the Lorentz transform. Do you understand that? It's kind of a very simple.
But they're not measuring the mass in the frame of the moving frame. They're measuring the mass when it hits a calorimeter in our frame. So in the stationary frame on Earth. So
well, there's some controversy about this, about whether there's actually a mass change. Okay. And, you know, if you go to Wikipedia, does mass actually change?
Well, there is mass change in our frame because obviously they're measuring it. I don't dispute the measurement.
Well, they're measuring an increase in the momentum that they detect when it slams into a detector. And the mass change is inferred. I'm not really want to get into that argument. The point I'm making is that the Lorentz transform is useful in relativistic dynamics because it gives them, it allows them to use the Newtonian equations, the equations that apply at low velocities in our normal world. They use those same equations modified by the Lorentz transformation. And when they do that, they get good answers that agree with the experiments. So they've changed the scale of the quantities that they're using in their equations by these beta factors. All right, we're coming up with, looks like 6 minutes. So did everybody understand the point about time didn't really change? That's one of his fundamental claims. That's one of the fundamental claims that they give, that time has changed. Time and space are changed. They're not really changed at all. That's an illusion of the mathematics that he's using.
Absolutely right. There is absolute space and absolute time. That's it. There is all these mathematical tricks. Forget about them.
Well,
let me tell you a few words.
They're useful, as I said, they're useful in doing calculations in certain areas.
I don't know these areas. Because the main meaning here, you told, I'm very sorry, let me tell you my opinion about it. That laws of physics the same in both frames. Absolutely wrong. Because laws of physics valid only for absolute cosmic medium, because all the physical laws depends on cosmic medium only, means it's absolute. There is absolute frame, and for absolute frame we have all the laws of physics. When we are going to some other frames, I don't know what you're talking about, what kind of laws of physics you have. You don't have them, because all laws of physics depends on absolute frame in conjunction with cosmic medium. Many times I told you about. That's why we don't have changed the laws. I don't know what do you mean. Because the main point is laws of physics, and they valid only for absolute frame of reference. And what is going on with the moving frame, I have no clue.
Well, that's a good point. The point I'm making is that once you understand what the mathematics is doing, it turns out that this mathematics maps to an absolute frame as a basic assumption, because once we have time and space defined in our absolute frame, then these transformations work correctly. Okay. Einstein doesn't have any absolute frame. He doesn't have any real, he doesn't really have any real anchor point for anything in his physics. It's all relative to something else. So we sort of taken away this mathematical approach solves a lot of the confusion that he's injected into by saying that time is different for motion. So if I'm moving, my time has changed because, according to him, his clock readings have changed.
Very sorry. What does it mean time in this theory? What does it mean time? Because time duration, we know you have one event and another one, you can measure time duration. But what is time in all these equations? T, what does it mean? I have no clue. It's a mathematics only for me. Time is some kind of parameter, fundamental parameter of what it is. It is time, solar time, universe time. What does it mean, this time, even the meaning of this, letter T, T3, T prime, T is what? What does it mean, T? It's mathematics only for me. There is no physics behind all these transformations.
That's the whole point, Vladimir. It's not.
Yes, you're absolutely right. You're absolutely right. I support you 100%.
We're talking about, what I'm talking about is what is the correct mathematics that you have to have before you can answer the questions that you're asking. So in other words, if we have the right mathematics, then we can.
You're absolutely right. If it's the wrong mathematics, don't even talk about it. This is my point. Forget about it. There is no theory because there is no even right mathematics for it. Man. And physically, as I told you, there is no meaning for this transformation at all because physical laws depends on the stable absolute frame of reference in conjunction with my cosmic medium. That's it, simple like this. You cannot talk about anything else when you started moving with your different frame. I don't know what do you mean. All these definitions wrong, absolutely wrong. I don't know what does it mean at all. That's why my understanding of special relativity, forget about it. It's all bullshit.
Well, yeah, because they have the wrong mathematics. Yeah.
That's one point. Another point, the main purpose is to prove that laws of physics the same in different frames. Wrong. Even this point is absolutely wrong.
Well, it depends on what you mean by laws of physics.
Laws of physics, it's laws of physics. They depend on cosmic medium only, on absolute frame of reference. That's it. We don't know any other laws of physics in a moving frame. We don't. I don't. Maybe you know. I don't.
Einstein's theory is an attempt to figure that out. Unfortunately, he did it wrong. And at this point, what I'm really basically pointing out is that you have to understand. Vladimir, you got interrupted. My point is that we have to have the correct mathematics before we can make it into a physical model. Okay. Yes. Now you can object to. Now, if you don't like Lorentz transformations, basically, all this work is a waste of time, I suppose. But that's Einstein's theory is basically accepted by the mainstream, and unfortunately, it's got too many mistakes in it. And so you hear people will say things like, "Well, according to Einstein, time changes due to motion." Okay, now I can understand your confusion at that because I don't think that's true. Okay, now asking about what time is, that's obviously a legitimate question. Time is what is measured by a clock, and essentially there's an agreed upon definition about what a standard clock is and what a standard time is. And that's kind of a human definition is defined by what people in government have decided time is. Okay, it's a legal agreement between nations, and they call that universal coordinated time, and that's what time is. Okay, to answer that question, time in physics, it's kind of just a definition actually. So, but if we're going to talk about Einstein's theory and getting the correct theory, we have to have the correct mathematics.
But there is no correct mathematics and there is no physics at all.
Yeah, well, what I'm proposing is that what I'm proposing is that this is a way to get the correct mathematics. I think this mathematics is correct. Okay, so if you have the correct mathematics, then you can find mistakes. Do you understand what I'm saying?
Yes, you're absolutely right. Let me ask you the question. 120 years passed, and nobody before you done the right mathematics. Why they don't know how to do mathematics? I mean, all these famous physicists, mathematicians, and all this stuff. Let me ask you the question. They don't understand what they are doing.
Well, I
I
can only
mean,
answer from my point of view. Okay, so I'll answer from my point of view. I didn't understand any of it. And I started reading all this stuff, and I read those papers. I talked about the papers. I couldn't understand any of it. Didn't make any sense to me. So I decided I had to figure it out by pencil. And I read math books and puzzled over this. And I read a lot of physics journals and I puzzled over this. And a lot of that is discussed in the first video that I did on this topic, where I discovered Hasio by I's paper, where he talks about the 4 transformations. And I thought, where did these 4 transformations come from? I mean, it came from Hasio by I and his paper. Okay. And until then, I had no clue that there were 4 transformations, not a clue. Okay, but he didn't have the full answer to what the 4 transformations are. He just showed that given his interpretation of the 4 transformations, he got the right answers. That's pretty astounding. Okay, now this was a paper that was published in Physics Essays in the 1990s. And apparently, nobody paid any attention to it, I guess, except for me. Then also in Physics Essays, I talked about this. Miru, Harada, and Sachs published a paper where they talked about that what the transformations did was they changed the scales. They were time scale transformations. Okay, and when I did more work on this, I found out that Dingle had actually proposed a similar idea that you have to define what the time scale is. Okay, what is the definition of your second? And so basically, these are ideas that that are out there that I just put together, and I studied math books. And when I studied math books, I realized that there's this idea of the basis and coordinate transformation, or linear transformation theory. Okay, but that doesn't exist in Einstein's theory, although he claims to be a theory of coordinate transformations, but it obviously wasn't a theory of coordinate transformations. And so basically taking math books and putting this together is really basically where this comes from. Okay, that's the origin of it. Now, one of the big things was this. I haven't really talked about this because this is very deep in the bowels of the math theory, that what Einstein calls inverse transformation is really what mathematicians call the dual transformation or the adjoint transformation, and it's in the dual space. And so what that means is that the T, the symbols T, don't mean the same thing in a coordinate transformation as they mean in a basis transformation, which is why the coordinate transformations are dial readings on the clock, and coordinate transformations is a transformation of the period or the clock period or the unit second. Okay, then once you have those 2 ideas, then that sort of tends to make it make sense. Okay, then you can put them together. Einstein did all this stuff before the mathematicians had invented any of these ideas. about coordinate transformations. He didn't know anything about any of that. But what's interesting is that nobody ever went back and corrected the theory. No mathematician ever went back and said, wait a minute, hey, this is wrong. They were perfectly happy using the Minkowski thing. Minkowski invented a special mathematics that made Einstein's theory work, or appear to work. It doesn't actually make his theory work because it still has the paradoxes in it. It still has the all the paradoxes, because you can't really solve the equations, because he mixes up coordinate and basis transformations. And when you mix up the coordinate and basis transformations, you don't get the right results. You get paradoxes. Okay, and so that's a lead in to, I'm going to talk about the Solari thing. And
Harry, before you go to Solari, can I add a comment?
Yes.
Okay.
Okay. So I've been trying to make a point for the last couple of months by email, and I'm clearly not making my point because no one seems to respond to it in a understanding way. But there's something missing from this analysis, which is that one of the fundamental assumptions of the Lorentz transformations and of special relativity is that the clocks within a moving frame do not report the same time of day. Einstein's term synchronization or synchronized clocks is not what we think it is. And if we look very carefully at his 1905 paper and look at the method that he uses to confirm that clocks are synchronized according to his method, the clocks do not report the same time of day. And I don't know, I seem to be saying this over and over again and nobody responds, but it explains everything. All of this confusion goes away when you understand that he's using clocks that are out of phase. There's two effects on the clocks. One is they tick at different rates, and the other is they've been calibrated so that they report different times based on their location along the axis of motion. And when you factor that in, and it's in the Lorentz transformations, there's two terms in each Lorentz transform. One of them is a clock tempo term, and the other is a term that calibrates the clock based on its location. And when you consider that, the math actually works.
Well, I don't understand any of that, so we'll just move on to what Solari did wrong.
Oh, dear.
But you think Solari did something wrong because you don't understand any of that. That's the point I've been trying to make.
I do understand it, Joe. That's exactly the problem. I do understand it.
I want to hear more about
And you don't accept, you and Stephen Gift don't accept that I do understand it.
Yeah. Okay. Hi.
Okay.
That's supposed to be called Einstein synchronization now. So
yeah.
Einstein synchronized his clock in a particular way. And then when you start arguing with people who are in relativity and supposed to know it all, they start saying that's the only way you can synchronize clocks.
Joe.
Correct.
So
Joe,
you go off on the tangent then.
Joe, were you speaking of specifically actual clocks, like synchronizing actual clocks, or were you speaking theoretically?
Well, Einstein was talking about synchronizing actual clocks, and he gave us a method for determining that clocks are synchronous according to his definition, which is completely the opposite of what we think of synchronized clocks. We think clocks reporting exactly the same time, right? He's talking about clocks that report different times based on their location on the axis of motion. And when you use that second term of the Lorentz transforms, the paradoxes go away.
Don't think so.
Okay.
No.
All right.
Hi. So no, that part of Einstein's paper got mistranslated from German into English, and he was only proposing that sort of way of doing the synchronization. He wasn't saying it was the only way of doing it. He was just saying he's going to do the mathematics based on that synchronization.
Oh, I agree 100%. And if you do the synchronization differently, which is the Solari way, you
Yeah.
get different math.
But
But you're using.
So
Sorry.
I've looked at Sorelli, and he's not saying that Einstein is wrong. And when you start asking questions about Sorelli transformations, and that's supposed to be a different way of thinking about special relativity. So you've got all these diversions. It's not a different.
Okay. Well, I will shut. I'll shut up.
Okay. Thank you.
Well,
I'll shut up.
I'll just say, Joe, I have no idea what you're talking about. And, you know, as far as I can see, Einstein made a gigantic mistake when he talked about clock synchronization. And the point I would make to you is he did away with that when he derived the Lorentz transformations by the algebraic method. And I made a point of bringing that up. No, don't shake your head. Don't shake your head. See, you're shaking your head. Okay,
Yeah.
that was
You can
just
shake our head.
all this synchronization stuff
He's
was
allowed
so
to.
he could derive the Lorentz transformations. Okay.
Well, I could say it the other way around, that Lorentz used the clock synchronization concept
Lorentz,
unknowingly.
no, Lorentz didn't have anything to do with clock synchronization as far as
I know he didn't know what he didn't know what it
Lorentz
meant.
was basic. Lorentz was looking for transformations that made Maxwell's equations invariant.
Correct. Yes. And he came up with these mathematical formulas that accomplished that. It was Poincaré and Einstein who said, you know what you did? You assume that these clocks are reporting different times a day, and that's why everything works.
Well, you know, this is a fundamental issue here. I'm just going to tell you this is what I think is the correct mathematics. If you want to use your mathematics and try to make it make sense using your mathematics, that's fine. I think this is the correct mathematics. I think Solari is wrong, and I'm going to tell you why. Okay.
Okay. Yep.
And you've already seen this and you don't agree with it. Well, that's fine. All right. My point here is, okay, so here's the Solari Tangerini transformations. Can we agree they're the same?
Tangerlini assumes that the clocks are absolutely synchronized, meaning they report the same time of day. Solari's saying you could do it however you want, and he included another variable to talk about the difference in the clock readings.
But the transformations that come out of it are the same for time.
If you use absolutely synchronous,
he gets the same. They get the same transformation formulas.
Yes, when you synchronize the clocks, absolutely, yes.
Well, they agree. They get the same transformation formulas. I looked at both papers. They're the same transformation formulas in both papers. Okay, and I don't think they're correct. And you can argue about this. Anyway, so Solari said that this is the problem down here. I say, unfortunately, Solari and Tangerini are incorrect. Why are they incorrect? Because they mix up the basis and the coordinate transformations. Okay, and I'm going to try to explain that here. Solari gives the inverse transformation for x prime equals beta x minus ct. And then he derives the inverse and he gets this inverse, x equals x prime divided by beta plus v beta t prime. This equation makes no sense. Do you understand this equation here? You see this here, the Solari says, you see this equation. Have you looked at that equation?
Yes, it does. It's just that T means something different to Solari than T means to Lorentz.
Well, that's not really much of an answer, but so we have a theory based on we don't know what T means.
Well, no, we do know what T means.
It's exactly
but it depends
my
on
point.
how you synchronize.
You don't know what you're talking about.
No, it's how you synchronize the clocks. T is defined as the time reported by the clocks.
Now you're lost in special relativity when you say it depends on how you synchronize.
Well, what are the two ways of looking at it? The two different ways.
Okay. In one way,
Joe, just let me go ahead here. I'm going to go ahead.
Okay.
We can argue about it later. Okay, so this equation here, I think, is wrong. Solari says this, x prime equals, I think, and it should be x equals x prime plus vt prime divided by beta. Okay. So I claim his equation is wrong. Okay. And he's got these time equations mixed up. So he's using coordinate equations and a basis equation. The equation that he uses for space is a, okay, so x prime equals beta t, this is the Solari equation, x prime equals beta x minus vt, and t prime equals t divided by beta. Okay, this first equation, x prime beta x, that's a basis change equation. The equation t prime over here, that's a coordinate change equation. And they're not going to go together. Okay. And then he gets for the inverse, he gives x equals x prime divided by beta v t prime. I don't know what beta b I don't know what this term here means. Beta t prime. What does beta t prime mean? That doesn't make any sense. Okay. And he has the t equals beta t prime inverse. So now he's associated this strange equation, we don't know where it came from, with this coordinate equation. Okay. Now, the time coordinate transforms seem correct because they're coordinate transforms, but the distance or x coordinate transform, he's using the basis transform out of the Lorentz transformation. That's you can't mix these things up. He's mixing them up. Okay, and then now we have their 8 transform pairs. Here I give it. X prime equals beta x, t prime equals beta t. Notice that they're consistent. The form of these equations is the same, and it's the rest going to moving. Then we have the other, which is the coordinate transformation. Notice here x equals beta x prime. These are consistent. Notice that they're in the same form. They're not in different forms. They're in the same form. X equals beta x prime. So we're moving along here. So we have all these. Now, how do we get these? We take the basis transform, and we change the symbols from prime to unprime. You see, that's what happens when we have the basis symbol. We have x. And then to get to the coordinate transform, we just move the primes. We go x prime x, x to x prime. That's really what's going on here in the mathematics. Symbols don't have the same meaning because Einstein thinks the symbols are the same. They don't have the same meaning. So the symbols don't mean the same thing in the coordinate transformations as in the basis transformations. I explained that before. Don't want to go over that. Again, does anybody have any questions about that? Basis transform changes the scale.
Well, I don't have a question about that specifically, though. As far as the 2 equations, and then you add 2 more with the Lorentz transformations, I don't understand. Well, the first 2 suggest time dilation, or that clocks run slower, and that the other 2 counteract or cancel that out. Is that at all the truth?
The total time turns out to be the number of seconds in an interval times the length of the tick of the clock, if you will, or the period of the clock oscillator. The clock oscillates and it counts each time that the clock oscillation occurs, or a tick, and it counts those, and it does a conversion into seconds. So it counts all these oscillations of a frequency oscillator and converts that into a count on the dial that is in terms of seconds. You understand that?
Why are any of the 4 equations necessary, though? The Lorentz transformations in general.
Why?
Yeah.
I'm not sure I can ask that. That's a philosophical question.
Well, it's also scientific. I mean, Jim asked earlier.
Well, what are you asking?
Well, I mean, as from what I've read many times, the Lorentz transformations were meant to account for the invariance of C, just as relativity was. Time dilation was theorized as part of that, which I don't agree with either.
Well, you're giving the Einstein interpretation.
Yeah, I mean, I don't agree with that, but the Lorentz, I mean, Lorentz believed in length contraction and mass increase. I mean, I don't see why the Lorentz transformations are necessary.
Well, you're asking a philosophical question.
So you'll just dismiss it because it's philosophical?
Physicists use these equations because they're useful to them.
Yeah.
Well, I've got an answer for Jerry. The Lorentz transformations, their main function is to divert attention from science and physics.
All right, okay. All right. Okay, so anyway, here's the point. I'm going to add back the VT terms. And so now we have these equations. X prime equals, this is a basis transformation going from the moving to the rest frame. Then we have the inverse transformation going from the moving frame to the rest frame. Okay, and this gives you all the equations. Okay, the point is Solari doesn't get those equations. He doesn't get the equation. These equations that you're supposed to get, these are the correct equations. Solari doesn't get the correct equations. So how can his theory be correct? That's my criticism of his theory. So they're telling us his theory is correct. How can it be correct if he doesn't get the correct equations? Okay, so I go through a lot of math here, and essentially dissect his equations and show that you really can't get the correct answer from his equations. So what he did was he mixed up the basis and the coordinate transformations in his theory. And according to what Hasio by I says, you can't do that. If you have to have the basis time, you have to have the time transformation has to be consistent with the distance transformation. So here, x prime equals beta x vt, t prime equals beta t. Now, this may seem a little bit strange, but you notice that the beta is the transformation, x prime is there. The transformation is consistent. T prime equals beta times t. Here's x prime equals beta x minus vt. They're consistent in their form. Okay. That's the whole point. When I calculate the inverse of this, I get I get x equals x prime plus vt prime divided by beta. So I get another pair of equations that's in the same form. And that also agrees with what I said back here in the beginning. Now, the problem with Solari is he doesn't get these equations. The equations don't appear in the same form. In other words, he's got this messed up equation that I show at the beginning. This x equals x prime divided by beta plus b vbt prime. What does vbt prime mean? I have no idea what that means.
Can I give you an answer?
Sure, give me an answer.
If you have to substitute t for beta t prime, according to Solari, and then it's vt.
Doesn't work in the math. That's the whole point.
Oh, it does. It gives you exactly.
It doesn't work in the math. That's the whole point.
How does it work?
It becomes the Lorentz transform. If you put in VT instead of V beta T prime.
No, it works the way I show it, which is you don't get these equations when you do it. Solari doesn't get the correct equations. Here are the correct equations. Solari doesn't get them.
Okay.
How do you explain he doesn't get the correct equations?
Well, you're assuming these are the correct equations.
No, I proved they're the correct equations.
Harry, you're really smart, and I like you a lot. But we're not communicating. We're talking past each other.
Do you mean
someday you and I should just have a conversation where we try to connect the dots.
Well, Joe, you're just objecting because you claim you have a different interpretation of what T means. I don't know what T means, so I can just only go by what the equations, the mathematics says. The mathematics says these are the correct equations. It doesn't say that Solari's equations are correct. You're saying that, well, if we interpret Solari's the time synchronization of the clocks and we have a different meaning of T, then his system works.
Correct.
I'm sorry, I just don't agree with that.
Okay.
I don't know what synchronization means according to Einstein. So that goes back to I don't know what it means. I don't think it means anything. I think it's just complete nonsense.
It means there's a phase difference between the clocks based on their location.
That doesn't mean anything to me.
It means that the clock in train station A reports a different time of day than the clock in train station B.
Yeah, but that's not how clocks work. All the clocks that I know of, they pretty much give me the same time.
I agree with you. I agree with you. And that's why special relativity is so weird, because they don't give you the same time, and Einstein forced that.
Well, in my theory, all the clocks give the same time, as I explained.
Yes.
So that's why it's the correct theory. All the clocks are running synchronously and they all report the same time.
That's great.
There's no difference between the traveling twin and the twin that stayed at home.
Well, I agree with you that time is the same. It's kind of a universal concept. But the twin paradox, if you just substitute heartbeat for tick rate or period, I think what they're saying is that our biological processes slow down the same way the clock slows down.
Well, yeah, but that's just an argument with no substance behind it.
I agree.
It doesn't mean anything. So what Einstein does, he starts off with a synchronization criteria, a hypothesis about the speed of light's the same. Then he has a synchronization criteria that he says synchronizes the clocks, which doesn't really mean anything to me. And then he derives a Lorentz transform, and then he comes off with this fakey math where he puts in x equals vt, doesn't explain why he put in x equals vt, again gets the magic transformation equation that says the clock is running slow. Yeah, okay, but it's really the hands of the clock that are changed. And then from that, because the hands of the clock are different, he says time is different. That doesn't convince me of anything.
You missed that. He assumes relative simultaneity instead of absolute simultaneity.
Yes.
And that messes everything up. Simultaneity is relative instead of absolute.
Well, that's because of his assumptions that he's making about the speed of light has to be the same.
But he supposed to give two assumptions in this paper, then he adds these extra ones.
Well, as far as I'm concerned, I have really no idea what he's talking about. Then he's got these inverse Lorentz transformation, which he's confused everything about. That's completely wrong. It's not an inverse transformation. It's the dual transformation.
Yeah,
Then he uses the dual transformation and gets all these paradoxes.
yeah. He's ambiguous as to what he's talking about, but the problems in special relativity are supposedly sorted out by mathematicians that came later. But of course, when you try to look into that, that's all ambiguous as well. It's supposed to be mathematicians like Max Born and Wolfgang Pauli, and
they didn't really change his theory. That's kind of, I know your presentation where you talked about that, but they're still using that same equation, which is that t equals beta t prime, which is
they're supposed to sort out the problems with the mathematics. And if you want to read them, it's not clear how they did any of that. It's just more ambiguity.
They adopted Minkowski's method, which is basically Lorentz transformations in disguise.
Yeah.
Can I ask you another question, guys? Because I don't understand what does it mean time in special relativity, and I don't understand what does it mean this letter C. What does it mean C?
You don't know?
I don't. Maybe you know, Jerry. Tell me.
C is the velocity of light, and time is the temporal order of existence.
First of all, speed of light in vacuum, I don't know what does it mean. First of all, there is no vacuum. There is some medium. The second very important point, there is no light. Light, what you can see, it's light. And electromagnetic waves, it's a little bit different story. We have right now radio waves between you and me. Speed of this radio waves, the same as speed of light, or what does it mean?
Well,
Guys, speed of light. We have some parameters. We're talking about mathematics. There is no logic in mathematics. There is no right mathematics even. What is the correlation between this wrong mathematics and real physics?
Would you say that light doesn't have a velocity?
I told you there are electromagnetic waves according to Maxwell equations. There are no light. Meaning, what does it mean light? Light, it's 400, 700 nanometers. You can see, Jerry, that's it. And what about the radio waves? We're talking with you right now through them. They're light or what?
Well, I think this is just another example of people who've adopted standard way of talking about things because of Einstein said that he has this postulate, the speed of light is a constant, and everybody said, oh, that's brilliant, and they just adopted this way of thinking about things.
120 years ago, how long we will hold this, bullshit, speed of light in vacuum? And we put this even speed of light in vacuum in Maxwell equation. We polluted them. We changed them at all, Why you touched Maxwell equation? They are ideal. Forget about them. And there is electrodynamic constant C in Maxwell equation. Take it as he proposed 170 years ago.
Vladimir, would you say that light has a velocity through air?
What? I'm sorry.
Would you say that light has a velocity through air?
Of course there is. But it's a different speed. Even in our light right now, we can see there are some changes because medium has some index of refraction, or that's it. Check it. Check it accordingly. You have different mediums. You have a different speed of electromagnetic waves. There is no particular meaning of light. Light, it's visible light. That's it. Very narrow wavelengths. That's it. Simple like this. Guys, there is no speed of light. And we are talking about the theory. We don't know what does it mean tau, time, and what does it mean c. We don't know. What we're talking, and what is important, I absolutely agree with Harry. It's wrong mathematics. What we're talking about, wrong mathematics with unknown letters, C, T, something like this, transformation. I don't care about it because there is no physics at all behind all these equations.
Well, even though we can't create a perfect vacuum, we can get close to it. I mean,
you are not God. You cannot create perfect vacuum. Forget it.
No, you can get
You're
close
not.
to it. You can get close. Or so you're just going to throw out the idea that C is a valid concept.
It's not valid. Because I told you many times, when you have a different medium, immediately you have your different speed of electromagnetic waves through this medium. There is some kind of ether, cosmic medium. You have different, speed of light, no, speed of electromagnetic waves. Maxwell, he didn't introduce light. He introduced speed of electromagnetic waves. And when he calculated the speed based on electrodynamic constant measured before him, he found, oh, by the way, this number very close to speed of light measured with some other guy from mountain to mountain. Okay, that's it, what he told. And his conclusion was simple. The light is electromagnetic phenomenon. That's it. That's it.
Well,
He never compared, he never replaced electrodynamic constant for speed of light.
maybe you have a valid point. I mean, maybe
Hold on. We're
Not
coming
my
up to the
point,
end
it is
here.
Maxwell's point.
All right, we're coming up to the end. Okay. And we got 2
Let me
minutes.
ask you the question. Did you publish this very good, results, review, paper? Did you publish these results by
Well,
yourself?
part of it is at the General Science Journal and different papers.
Do you
And
have any response for this
no,
absolutely right paper?
no. Okay.
Thank you so much. It means that cheating all of us. I mean, all these orthodoxies, all the famous guys, they know nothing about time, they know nothing about speed of light, and they know nothing about the right mathematics. You published already. Good. We are in a crazy house, and where we are in physics, I don't know.
The whole point is really basically what I'm trying to do is I'm trying to summarize some of the ideas. And Einstein made a big mess, and then Minkowski came along and changed it, made it look like there was an actual mathematics that went along with what he said, but they never did get rid of all the paradoxes and all the nonsense. And so people, when we talk about it, we're just confused because it's just confusing. The mathematics behind it's not really correct. Then you have this guy Solari comes along, and then Stephen Gift comes along and says Solari's right. We all should adopt Solari, but there's this equation that I'm talking about, it obviously looks wrong. No explanation why he's got this wrong looking equation in there. I can't really make any sense out of what he's talking about. It's just me, we're supposed to adopt a Solari theory, which is just another mess of a theory to replace the Einstein mess of a theory. So what are we doing